For this one, I thought we would do a controls example. I haven't done one of these in a while. And I just picked out a Routh array problem because I don't think I've ever put one of these on the YouTube channel. So let's go ahead and let's look at this one. So we've got this closed loop transfer function already given to us. This is a 4 right here. So notice the polynomial in the denominator is a 5th order polynomial. And like I said, this is already a closed loop transfer function that's given. And we know that because it's T of S. If it was just the regular open loop transfer function, it would be G of S. Okay, and it says how many closed loop poles are located in the right half plane, left half plane, and on the j omega axis. All right, and we're going to use Routh's array to do this, just because it's a good little method to know how to do. All right, and let's put that on here. So we'll use Routh array to solve. Okay, so first of all, to set up our Routh array, let's go ahead and get that going. We want to look for the order of the polynomial we're looking at, right? So this is the 5th order, so we're going to start with s to the 5th, and then we're going to go all the way down until we get to s to the power of 0. Put a line there, and then we're ready to start filling in the top 2 rows of the array. All right, so what we're going to do is we're going to look to the top here. This is s to the 5th. We want to pull off the coefficient that goes along with that. So that's going to be a 1, all right, because it's just s to the 5th. So we would put a 1, and then we're going to go every other term. All right, so we started here. We're going to jump to this one. So we get -7 next. And then we're going to jump to the next one, so -18. Okay, we're done with the top row now, because we're out of values. All right, now we go to the s to the 4th row. All right, and again, we want to start with the coefficient that goes with this term. So right here. So that coefficient is a 1. And then we do every other one. All right, so we're here. We're going to jump to here, -7. And then from -7 to -18. All right, well, now looking at this, I already see an issue, right? We have the same exact thing on these 2 rows. So I know by looking at this already, I'm going to get a row of zeros down here, but let's go ahead and prove that. Let's show the calculation. So remember when we're doing the Routh array, when we're below the top 2 rows, we have the little determinant equation we're going to use to find our values. So let's do that. So for this one right here, we're going to have -1 over 1. All right, because remember it's always negative. And then we're going to put the determinant of 1, 1, -7, -7. Just like that. And by the way, in case anybody's wondering, because I forgot to mention it, we got the -1 over 1. So remember, for this term right here, it's always negative. It's always going to be a 1 in the numerator. The denominator will be this value that's in the row above where we're working. So I'm trying to find this value, so I'm going to use this value in the denominator. Okay, and then we go through and do the determinant. All right, so we got -7 minus a -7, and then that's going to give us a positive, right? Let's put this down here. So we got 1 times -7 minus the 1 times -7. So these become positive, so that's a 0 right there, and then you get the -1 over 1. All right, so that's 0. And then we're going to get this similar thing for this next element here, but let's write it out. So again, this first fraction is -1 over 1, okay, because we're always going to use this first element in the row above. And then we're going to use this first column, 1, 1, and then now we go to the second, or not the second, the third column here, so -18, -18. Okay, so same kind of thing here. So we're going to have 1 times -18 minus 1 times -18, and that's times the -1 over 1. So notice again, we've got -18 plus 18, so it's 0. Okay, so a row of zeros, just like we kind of knew it would be, right? Because these 2 rows were exactly the same. You'll also get the same thing if you have a multiple of one of the rows. Like if I had this row and then all of these elements were 2 times these elements, you're going to get a row of zeros. Okay, So now we've got this row of zeros. So this is called, you know, a special case number 2 type situation because we have a full row of zeros here. So what we want to do is we got to find our polynomial. Okay, so let's just call this P of S. And what we're going to do is we're going to look to the row above to get this polynomial. Okay, so the row above starts, you know, is the S to the 4th row. So I'm going to use that to create my polynomial. And this is going to be our even polynomial or auxiliary polynomial, whatever term you want to use. So this coefficient of 1 goes with S to the 4th. So I'm going to have 1 times S to the 4th. And it's an even polynomial, right? So that means this term, the -7, is the coefficient for S squared. And then the -18 is technically the coefficient for S to the power of 0, right? And S to the power of 0 is 1, so I don't need to write that. But notice all the exponents are even because it's an even polynomial, okay? And then that we have that, what we need to do is I need to use this to replace these zeros. Okay, I have 2 zeros here, so I need 2 values. What we're going to do is we're going to take the derivative of this polynomial with respect to S, and then that's going to give us our coefficients we need to replace these zeros. All right, so what do we have for the derivative here? Well, derivative of S to the 4th is going to be 4S cubed. And then this one will be -14s, and then derivative of -18 is 0. So now the 4 and the -14, those will replace those zeros. Okay. Now, how do you know which one goes where? Well, let's look. This is the S cubed row. This is S cubed, so the 4 replaces that one. And then this -14 goes right there. Okay. So remember, when you're doing these problems like this, using this Routh array, you should only get a row of zeros in an odd exponent row. And the reason for that is because you have to look to the row above and get an even polynomial, which means all of your exponents are even numbers. So if you somehow get a row of zeros in like the S squared row, you've done something wrong because it doesn't make sense to use the odd exponent rows to get your polynomial. Okay, it's got to be even exponents in that polynomial. So row of zeros should only be on the odd exponent rows. Now that we've got the 4 and the -14, we're going to use these values just like we would a regular value, and we're going to continue filling out the rest of this array. All right, so let's do this next one. So the S squared row. So now I'm going to have -1/4, and then in the determinant I'm going to have 1, 4, -7, -14. Like that. And if you do the, the little calculation here, you're going to end up getting -3.5. All right, so you get -3.5 there, and then now let's do this one. So this fraction here is not going to change while we're working on this same row. So we still have -1/4. This first column here doesn't change, so it's still 1, 4. Now the second column does change. Now I want to move to this area right here. So I'm going to have -18. And then this is a 0, right? So we just, because nothing's there, so let's plug in a 0. Okay. Now when we do the calculation, we're going to get 0 minus 4 times -18, and then that's times -1/4. So this is -18. Okay, and then that's all we can do because we've already used all the elements over here. So now we go to the next row. So -1 over -3.5, right? Because that's the element above. The determinant will be 4, -3.5, -14, -18. Okay, and then keep writing off the screen here. And then solve that, you get -34.57. Right, and then that's going to go right here. Okay, And that's all we're going to have for this row because I don't have any values here, right? Be 2 zeros, so we don't have that one. And then this bottom one right here, last one, we're going to have -1 over -34.57. In the determinant, the first column will be -3.5, -34.57. And then second column, we got -18 and 0. That is going to equal -18. Okay. Now, did you notice a little pattern? So let's look here. So I got -18 there, right? Even exponent row. I got a -18 here, even exponent row, and a -18 here, even exponent row. All right, so that is a pattern. So on all of these arrays, assuming you do all the calculations correctly, the last element on any even exponent row will always be the same. All right, so this one here, the -18, was given from the polynomial itself, right? So technically, I didn't need to actually go through and do this calculation here, for instance, right? Because I knew already this was going to be -18. Same thing with this. Okay, so that will save you some time if you remember that pattern. Okay, now that's only for the even exponent rows. Okay, so keep that in mind. It'll save you a little bit of time on tests if you don't have to go through and calculate that. All right, and the reason for that is we always have to put in this 0 on these last elements for the rows with the even polynomials. So it's like that every time. So you can see we got a 0 here, 0 here, and that's what kind of ensures we're going to get the same value every time. All right. So now with this, we got our array set up. It's ready to go. So now we're going to look at this and we're going to figure out how many poles are in the right-hand side, left-hand side, or on the j omega axis. Okay. Now when we're doing this, what you're going to do is we're going to focus on the first row, or not first row, the first column only. All right, so all I care about when we do this is this first column. Okay, I don't care about any of this now. I'm going to look at this. Okay, and what you need to do is we're going to divide it up into 2 sections. Okay, so we want to locate where our row of zeros is. All right, so here's the row of zeros. Okay, and then we want to analyze the values below that line and then above that line. We're going to analyze them separately. Okay, so our auxiliary polynomial row, oops, let's put row, and below. Okay, so this will be s to the 4th and down. Okay, so here's our auxiliary polynomial row and down. And remember, the auxiliary polynomial row is just the row above the row of zeros. Okay, so we've got that. Now the auxiliary polynomial, which is right here, how many roots does that give us? Like if I were to set this to 0, how many values of s would we find? We would find 4, right? And we know that because of the exponent. Okay, so this one provides 4 roots. So now we know we got 4 roots from here. Now next thing we want to do is we want to count our sign changes. All right, so the sign changes are going in between the rows, right? So like I'm starting here and I want to look for sign changes from here down. So this is positive, right? So positive to positive, and then I'm going positive to negative. So this would be a sign change. So let's put a check mark. And then we're going negative to negative, no sign change there, negative to negative, no sign change there. All right, so I have 1 sign change. Okay, now what does that tell us? Well, anytime we have a sign change, that means we have a root on the right-hand side. All right, so we've got 1 right-hand side root. I know that. Okay. Now, the special thing about these even polynomials is there has to be symmetry with the roots. So if I've got a right-hand side root here, due to symmetry, I have to have one on the left-hand side. Okay, so that means I've got one left-hand side root. Okay, so again, this is due to symmetry, which is a requirement of the even polynomial. Okay, now that's only two roots, right? 1 plus 1 is 2, so I've got two more roots. Okay, I only had one sign change though, so that means I can't have another root on the right hand side, right? Because there was not a sign change for that, which means then, you know, you can't have on the left hand side. So I can't have two more on the left hand side because there's got to be symmetry. If there's one on the left hand, there's got to be one on the right hand. I don't have another sign change for a right hand side root. So that means what has to happen is I've got roots on the j omega axis, right? So that's where those other two roots will be. So essentially what that means is you're going to figure out where your row of zeros is, okay? You're going to look above, you're going to count the sign changes, you know, from here down, and then the number of sign changes you have tells you the number of right-hand side roots as well as left-hand side because of symmetry. And then all of the other ones from here down that have to be accounted for would be on the j omega axis, if that makes sense. Because, like I said, you have to have symmetry. So you have to have one on the right-hand side, one on the left-hand side in order for them to be on the real axis. Okay? So if you don't have any sign changes, then that means everything's going to be on the j omega axis. All right, so that's how you analyze this first grouping, you know, with the auxiliary polynomial row and down. And then this gives us 4 roots. But how many roots do we have in total? Well, if we look right here, this is a 5th order, right? So we have 5 total roots. So we have 1 root right now that is not accounted for, so we need to look at that. So now we're going to look at the other rows. All right, so we're going to look above the auxiliary polynomial row. All right, so s to the 5th to s to the 4th. Okay, and then this will help us figure out where this other root is. So now we're looking, it's a different color here. So now we're looking right here. Okay, and again, you're going to look for sign changes. Is there a sign change? No, no sign change there. All right, so we have no sign change for this region because it was positive to positive. So that means we've got 1 root left, okay, and it's got to be on the left-hand side. And that's because there was no sign change. If there's a sign change, it would be on the right-hand side. But if there's no sign change, it's going to be on the left-hand side. All right, so then we can kind of combine all this together. So we've got 1 on the right-hand side, and we've got 1 plus 1 on the left-hand side, so 2 left-hand side, and then 2 on the imaginary axis. So that gives us a total of 5 roots, which is what we needed to look for. Okay? So that's kind of how you do one of these with the row of zeros. All right, the trickiest thing usually for students is this part right here. So just remember, with a row of zeros, you're looking for symmetry, okay? So if you've got a sign change, you got 1 on the right-hand side, 1 on the left-hand side, right? They go together. And then everything else would be on the j omega axis, okay? If we had 2 sign changes, we'd have 2 on the right-hand side, 2 on the left-hand side, okay? So you got to have that symmetry. And that's just a function of the auxiliary polynomial, okay, that has all the even exponents. All right, so hopefully that one was helpful. I will see you guys next time.